What if I told you that the ground beneath your feet isn't actually solid? That the now you're experiencing doesn't exist for someone on Mars? That every GPS navigation bringing you home depends on time running at different speeds? Welcome to the bizarre reality of space-time, a concept so fundamental to modern physics that we literally couldn't function without it, yet so poorly understood that even its discoverer doubted his own creation. Here's what makes this truly mind-bending. We've built billion-dollar industries on space-time. We've photographed it warping around cosmic monsters. We've measured its ripples traveling across the universe. But ask a physicist, what is space-time? And you'll get an uncomfortable silence. Think about that. We can use it, we can measure it, we can predict it, but we cannot explain it. By the end of this video, you'll understand why this paradox exists, why it terrified Einstein himself, and why solving it might reveal that everything solid, permanent, and real about our universe is actually an elaborate quantum trick. Before we dive in, if cutting-edge physics mysteries excite you, hit that subscribe button and tap the bell. Your support helps me bring you more mind-expanding content like this. Drop a comment below with what confuses you most about physics. I read every single one. Let's begin with a patent clerk who broke reality. While the world worried about horse manure piling up in city streets, a 6-year-old nobody working in a Swiss patent office published 4 papers that would obliterate 200 years of scientific certainty. Albert Einstein wasn't a professor. No university wanted him. He spent days approving patents for electromagnetic gadgets and nights dismantling the universe. His miracle year produced 4 revolutionary papers: proof that atoms exist, the foundation of quantum mechanics, and 2 papers introducing what we now call special relativity, the revelation that space and time aren't separate entities, but fuse into a single 4-dimensional fabric. The core insight sounds deceptively simple. Light speed never changes, regardless of your motion. This seems impossible. Board a train traveling 100 kilometers per hour and throw a ball forward at 20 kilometers per hour. Someone on the platform measures the ball at 120 kilometers per hour. Speeds add. Common sense. But light defies this. Travel on a spaceship at half light speed and shine a flashlight forward. Logic says the light should move at 1.5 times light speed relative to Earth. It doesn't. Both you and Earthbound observers measure exactly 300,000 kilometers per second. Always. Identically. Impossibly. Einstein's solution demolished intuition. Space and time flex to keep light speed constant. Move extremely fast, your clock literally ticks slower compared to stationary observers. Distances physically compress in your direction of travel. These aren't illusions, they're measured facts. Unstable particles that decay in microseconds survive dramatically longer in accelerators when traveling near light speed. Atomic clocks flown on airplanes show measurably less elapsed time than ground-based twins. The difference? Nanoseconds, but perfectly matching Einstein's predictions. The implications shatter everything. No universal now exists. No cosmic clock ticking identically everywhere. When you claim something occurs right now on a distant star, that statement becomes meaningless. Different observers at different speeds would fundamentally disagree about what simultaneous means. Time isn't a river flowing uniformly for everyone. It's a dimension like height or width that stretches and compresses. This was Einstein's special relativity. Revolutionary, universe-breaking, but incomplete. It only described constant motion. It couldn't handle acceleration. And critically, it couldn't handle gravity, the force that makes apples fall and planets orbit. Newton's gravity had worked brilliantly for 2 centuries, but Einstein realized it contained a fatal flaw. It worked instantly. If the sun vanished, Earth would immediately spiral away, according to Newton. But Einstein had just proven nothing travels faster than light. Gravity couldn't work faster either. This problem would haunt Einstein for 8 years, and the solution would make him the most famous scientist alive. Drop a comment. What surprised you most so far? November 1907. Einstein sits in his Bern patent office, thinking about gravity, when inspiration strikes the happiest thought of his life. He imagines a construction worker falling from a roof. During free fall, the worker experiences weightlessness. Drop a hammer, it floats beside them, falling identically. From the worker's perspective, they're not falling at all. They're floating while Earth rushes upward. This seems obvious now. We've all seen astronauts floating in space stations, but Einstein's insight went deeper. You cannot distinguish between floating in deep space, zero gravity, and freely falling in a gravitational field, maximum gravity. He called this the equivalence principle. Gravity and acceleration are indistinguishable. They're the same phenomenon. Imagine yourself in a windowless elevator. Feel heavier? Either you're accelerating upward or sitting in stronger gravity. No experiment can distinguish these scenarios. They're physically identical. This unlocked everything. If gravity equals acceleration, and special relativity proves acceleration affects spacetime, then gravity must warp spacetime itself. Stand on Earth's surface, you're constantly accelerating upward, pushed by the ground beneath your feet. This means time runs slower at ground level than at higher altitudes where gravity weakens. This prediction sounds absurd, yet it's measured daily. Atomic clocks on mountaintops run faster than sea level clocks. GPS satellites experience weaker gravity. Their clocks gain 45 microseconds daily compared to Earth. Subtract 7 microseconds lost from their orbital velocity, and net plus 38 microseconds per day. Ignore this? Your GPS drifts 11 kilometers daily, becoming useless within hours. Every navigation app relies on Einstein's warped time. But Einstein wanted more than predictions. He demanded understanding. What is gravity if not a force? What is this space-time that bends? For 8 brutal years, 1907 to 1915, Einstein wrestled with mathematics beyond his training. Differential geometry, tensor calculus, concepts he'd never studied. He learned from mathematician friends, published preliminary versions, retracted them, made mistakes, started over. He later wrote to a colleague, "Compared to this problem, the original theory of relativity is child's play." November 1915. Einstein completes his masterpiece, General Relativity's field equations. Their beauty lies in elegant simplicity. Space-time curvature tells matter how to move. Matter tells space-time how to curve. Picture space-time as a stretched rubber membrane. Place a bowling ball on it, the membrane curves, creating a depression. Roll a marble nearby, it doesn't travel straight. It curves toward the depression, spiraling inward. That's gravity. Not a force yanking objects together, but objects following the straightest possible paths through curved spacetime. Earth orbits the sun not because of pulling forces, but because the sun's mass curves spacetime, and Earth simply follows that curve. Physicist John Wheeler summarized it perfectly. Spacetime tells matter how to move, matter tells spacetime how to curve. But embedded in Einstein's beautiful equations lurked something he'd spent decades trying to disprove mathematical monsters called singularities. If this is blowing your mind, smash that like button and let me know in the comments what you want explained next. Einstein's equations made a radical prediction. Massive objects curve spacetime so severely that even light with zero mass must follow the curves. Newton's gravity couldn't bend light. Light has no mass. Gravity shouldn't affect it. Einstein calculated starlight grazing the sun should deflect by exactly 1.75 arc seconds, roughly a quarter's width viewed from 3 kilometers away. Tiny, but measurable. Only one test existed. Photograph stars near the sun during total solar eclipse when its glare vanishes. Then compare positions to nighttime photographs when the sun is elsewhere. The 29th of May 1919, British astronomer Arthur Eddington led an expedition to Principe Island off West Africa. Heavy clouds threatened disaster, but during totality, 2 minutes, 36 seconds, they parted. Eddington photographed the stars. Back in his lab, measurements revealed stars had shifted. Light bent exactly as Einstein predicted. News reached Einstein via telegram. Eddington found star displacement at rim of Sunday. Einstein's response? I knew the theory was correct. Not arrogance, mathematical confidence. Einstein once said, if experiments contradicted his theory, I would have felt sorry for God, because the theory is correct. Newspapers worldwide exploded, Einstein proves Newton wrong. Overnight, Einstein transformed from respected physicist to global celebrity. Magazine covers, lecture invitations, scientific immortality. General relativity passed every subsequent test, explained Mercury's orbit wobble that baffled Newton, predicted gravitational lensing, distant galaxies bending light from objects behind them, predicted gravitational time dilation confirmed billions of times. But buried in Schwarzschild's 1916 solution lurks something disturbing. Karl Schwarzschild, serving on WWI's Russian front, found an exact solution for spacetime around a spherical mass. Elegant, but containing a strange radius where equations broke, producing infinities, singularities, mathematical nonsense. For the Sun, 3 kilometers. For Earth, 9 millimeters. These seemed meaningless. The Sun spans 700,000 kilometers, Earth 6,370 kilometers. The singularities appeared deep inside physical matter where vacuum solutions didn't apply anyway. Most physicists ignored it. Mathematical artifact. Nothing more. Einstein certainly did. He actively argued against singularities for decades, publishing papers attempting to prove they couldn't form naturally. But 1939 changed everything. Robert Oppenheimer and student Hartland Snyder proved mathematically massive stars, after exhausting nuclear fuel, would collapse past the Schwarzschild radius with nothing stopping them. No pressure, no force could prevent it. They'd become what we now call black holes regions, where space-time curves so extremely that light itself cannot escape. At the center, a singularity of infinite density, where physics breaks completely. Einstein died in 1955, still rejecting black holes. He was wrong. We've now photographed them. April 2019. The Event Horizon Telescope revealed the first black hole image, the supermassive giant in galaxy M87, exactly as Einstein's equations predicted. The monsters are real. Subscribe for more physics mysteries. Hit that notification bell so you never miss an upload. Einstein's equations predicted something extraordinary. Accelerating masses create ripples in space-time traveling at light speed. Gravitational waves. For a century, this remained theoretical. The ripples are unimaginably faint. Einstein himself doubted we'd ever detect them. Then came LIGO, the Laser Interferometer Gravitational Wave Observatory. 2 facilities, Louisiana and Washington State, each splitting laser beams down perpendicular 4-kilometer tunnels, bouncing off mirrors, recombining to create interference patterns. When gravitational waves pass through, one arm stretches while the other compresses. The effect? Smaller than 1/10, 0th a proton's width across 4 kilometers. Imagine this scale. If the distance to our nearest star, 40 trillion km, changed by a human hair's width, LIGO would detect it. The 14th of September 2015, 5:51 a.m., first day of LIGO's upgraded science run. A signal arrived. Louisiana first, then Washington 7 milliseconds later. The pattern lasted 0.2 seconds frequency, rising from 35 Hz to 250 Hz before abruptly stopping. This signature matched 2 black holes, each to 30 solar masses, spiraling together for billions of years. In the final fraction of a second, they orbited hundreds of times per second at light speed fractions. The merger released more energy than all observable universe stars combined for that instant. 3 solar masses converted purely to energy, radiating as space-time ripples. The event occurred 1.3 billion light-years away. The waves traveled 1.3 billion years to reach us, stretching LIGO's arms by 1/1000th a proton's width. LIGO detected it. The 11th of February 2016. The announcement revolutionized astronomy. Direct evidence we'd caught space-time vibrating. Since then, dozens more detections. Black hole mergers, neutron star collisions, Each teaches us about these extreme objects and gravity's nature. August 2017 brought something special. 2 neutron stars merging 130 million light-years away. Unlike dark black holes, neutron stars glow. Their collision created a kilonova visible explosion. Within seconds of LIGO's detection, alerts reached telescopes worldwide. Within hours, they found it. A new bright source in galaxy NGC 4993. The first multi-messenger astronomy event witnessed in both gravitational waves and light. Observations confirmed a long-suspected truth. Heavy elements gold, platinum, uranium are forged in neutron star mergers. The explosion scattered material worth Earth's weight in gold across space. Every gold ring, every gold bar exists because neutron stars collided billions of years ago, before our solar system formed. That scattered gold mixed with gas and dust, eventually incorporating into the disk, forming our sun and planets. You were atoms forged in stellar catastrophe. Each gravitational wave detection proves space-time's reality. It exists, bends, ripples, exactly as Einstein predicted. But here's the paradox. Detecting gravitational waves confirms space-time behaves as calculated. It doesn't tell us what space-time is. It's like detecting sound waves in air. You can measure waves, study properties, use them for communication, but measuring sound doesn't reveal air's atomic composition. Measuring gravitational waves proves space-time vibrates. It doesn't reveal the fabric's fundamental nature. That mystery remains unsolved. Share this video if it changed how you see reality. Let's get more people questioning the nature of space-time. Here's where everything breaks. General relativity says space-time is smooth, continuous, deterministic. Given current conditions, Einstein's equations predict future and past with perfect accuracy, limited only by computational power. Simultaneously, quantum mechanics says reality is probabilistic, discontinuous, fundamentally uncertain. You cannot know a particle's position and momentum precisely. Particles exist in superposition, multiple states simultaneously until measured. These theories are humanity's most successful scientific achievements. General relativity governs stars, galaxies, the cosmos. Quantum mechanics governs atoms, molecules, chemistry, all modern electronics. They fundamentally contradict each other. The conflict explodes when you quantize space-time itself. If space-time curves and ripples, it should be quantized composed of discrete units, like everything in quantum theory. There should exist a smallest possible distance, Planck, length to 10, -35 meters, and smallest time, Planck time to 10, -43 seconds. But attempting to quantize general relativity produces catastrophe. The equations explode. Infinities everywhere. Mathematical nonsense. Physicists have spent nearly a century trying to merge these theories. String theory, loop quantum gravity, causal set theory, all attempts to create quantum gravity. None have produced testable predictions. This conflict appears everywhere. Gravitational waves are perfectly smooth ripples, pure general relativity. But black holes producing those waves contain singularities that should trigger quantum effects. Space-time should foam at Planck scales full of quantum uncertainty. Yet detected gravitational waves are smooth. Where's the quantum foam? Then there's quantum entanglement, Einstein's spooky action at a distance. When particles entangle, measuring one instantly determines the other's state, regardless of separation. Einstein hated this. It seemed to violate his cosmic speed limit, information traveling faster than light. Experiments confirm entanglement is real. This creates paradox. If space-time is the fabric through which information travels, how does entanglement work? Particles are separated by space, yet remain instantly correlated. Some physicists now suggest entanglement is more fundamental than space-time itself. Space-time might emerge from quantum entanglement. Geometric relationships we perceive as distance and duration are actually patterns of quantum correlation. If correct, space-time isn't fundamental. It's an illusion emerging from deeper quantum processes. This leads to physics' most disturbing idea, the holographic principle. 1,970 seconds. Stephen Hawking proved black holes emit radiation and evaporate. This created paradox. What happens to information about everything falling into the black hole? Does it disappear, violating quantum mechanics? Physicists realized information never enters the black hole. It's encoded on the event horizon, the two-dimensional surface surrounding the black hole. The three-dimensional volume is merely a projection of two-dimensional surface information. If true for black holes, perhaps true for the entire universe. We might inhabit a hologram. Recent breakthroughs in quantum island calculations suggest information is preserved in black hole evaporation, but scrambled so thoroughly it's nearly impossible to extract. This resolves the decades-old information paradox. The resolution points towards something profound. Space-time and gravity aren't fundamental. They emerge from quantum entanglement. The fabric of space-time is woven from quantum correlations. Understanding this connection completely would give us quantum gravity. Comment below. Does this make space-time less real or more fascinating? Let's discuss. Let's discuss the twin paradox, one of relativity's most famous thought experiments, revealing something deeply disturbing about time. Alice stays on Earth. Bob boards a spaceship accelerating to 99% light speed, travels to a star 10 light years distant, returns. From Earth's perspective, Bob's journey takes to 20 years. 10 out, 10 back, plus acceleration time. From Bob's perspective, time runs slower. Returning to Earth, he's aged merely to 3 years. He's now 17 years younger than Alice. This isn't theoretical, this is what happens at extreme speeds. Time genuinely passes differently for Bob than Alice. Both perspectives are correct simultaneously. There's no absolute answer to how much time passed. It depends on your reference frame. But here's the disturbing implication. If time is relative, and different observers experience different durations between identical events, in what sense does time flow? Einstein's equations suggest past, present, and future exist simultaneously in what physicists call the block universe. Space-time is four-dimensional structure. Time is another dimension, like width, length, height. Your entire life, birth to death, already exists as a four-dimensional world line stretched through space-time. You're not moving through time. Time is a direction in space-time. Your consciousness simply experiences different slices sequentially, one moment at a time. Your future self already exists, out there in space-time, just at different coordinates. Profound philosophical implications. If the future already exists, what about free will? Are your choices predetermined, written into space-time structure? Physicists constantly debate this. Some say block universe is mathematical formalism, not literal. Others say it's relativity's most natural interpretation. We must accept that now is an illusion. Gravitational time dilation makes this stranger. Time runs slower in stronger gravitational fields. Stand at a black hole's event horizon, somehow surviving tidal forces, and watch someone far from the hole you'd see them in fast forward. From their perspective, you'd appear frozen. Approaching the event horizon, time dilates so severely you'd watch the entire future universe unfold above you. Stars born and dying, galaxies colliding. The universe aging trillions of years while you fall the last meters toward the singularity. But from the outside observer's perspective, you never cross the horizon. You appear to slow down, getting dimmer and redder, frozen forever at the edge. Which perspective is real? Both? Neither. Relativity says there's no absolute answer. This is where quantum mechanics contradicts general relativity again. Quantum mechanics treats time differently as an absolute parameter, not a flexible dimension. Reconciling these views remains unsolved. Time might not be what we think. It might be emergent, illusory, or something we can't yet comprehend. Like this video if it changed how you think about time. Subscribe for more reality-breaking content. We've reached the core mystery. What is spacetime fundamentally? Einstein's equations describe how spacetime curves responding to mass and energy. They calculate curvature given matter distribution. They predict object motion through curved spacetime, but they don't reveal what's spacetime is. In Einstein's theory, spacetime is a smooth continuum. Zoom into any point, there's always more space at smaller scales. Divide time into smaller intervals, there's always more time. Infinitely divisible. This works perfectly for observable scales. But there's reason to believe it can't be the complete story. Quantum mechanics says almost everything in nature is discrete, quantized coming in chunks rather than continuous. Energy comes in quanta. Light comes in photons. Electron spin takes discrete values only. The quantum world is fundamentally grainy, not smooth. This suggests space and time might also quantize at extremely small scales. A smallest possible length, the Planck length, to 10, -35 meters. A smallest possible duration, the Planck time to 10, -43 seconds. Below these scales, smaller distances or shorter times become meaningless. To grasp this scale, a proton is to 10, -15 meters. The Planck length is 20 orders of magnitude smaller. If you scaled a proton to observable universe size, the Planck length would equal a tree. At this scale, quantum effects on spacetime itself should dominate. Einstein's smooth fabric should break into something else, something grainy, chaotic. Physicists call this quantum foam, the idea that zooming in far enough reveals spacetime looks turbulent, bubbling with quantum fluctuations, constantly forming and dissolving tiny structures. But we cannot probe these scales directly. The Planck length is so small, we can't build experiments to measure it. Required energies would be to 10, 19 GeV. The Large Hadron Collider reaches to 14,000 GeV, about 10, 15 times too weak. Building a Planck-scale accelerator is far beyond foreseeable technology, perhaps beyond physical possibility. So, we're stuck using pure theory, mathematics, indirect reasoning. Several competing ideas exist, none directly testable. Loop quantum gravity quantizes Einstein's equations directly. Spacetime is woven from discrete loops about Planck length size. Connected in networks, area and volume are quantized, they come in discrete units. This might eliminate singularities, replacing them with quantum bounces. Problem: mathematically complex, hard to extract, testable predictions hasn't successfully unified with other forces. String theory. Fundamental objects aren't point particles, but tiny vibrating strings. Different vibrations equals different particles. One vibration is the graviton, carrying gravitational force. Spacetime emerges from string interactions in 10 or 11 dimensions, extra dimensions compactified at Planck scales. String theory is mathematically elegant, naturally includes gravity, unifies all forces, but it has to 10, 500 possible versions depending on extra dimension compactification, landscape problem. Which one is our universe? Unknown. It also predicts supersymmetry not yet detected at LHC. Emergent spacetime. Most radical idea, spacetime isn't fundamental at all. It emerges from quantum entanglement patterns at deeper levels. Distance and duration are illusions appearing at large scales, like temperature emerging from molecular motion. The bottom line, we don't know what spacetime is made of. We have equations describing its behavior, we can measure curvature, we can detect waves moving through it. But the fundamental nature of the fabric itself remains mysterious. Drop a comment. Which theory do you think is correct? Let's discuss. So let's return to where we started. Spacetime, Einstein's revolutionary idea, modern physics foundation. The framework describing gravity, cosmic expansion, black holes, gravitational waves, the Big Bang, an idea tested thousands of times, never failing. We use it daily in GPS satellites, cosmological understanding, surrounding technology. Yet the fundamental mystery persists. We don't know what it's made of. We don't know if it's fundamental or emergent. We don't know what happened at the Big Bang when equations predict a singularity key y where physics breaks. We don't fully understand whether black holes preserve or destroy information, though we're close to answering. We have equations describing behavior, but lack complete theory explaining true nature. This isn't failure. This is where we are. This is human knowledge's frontier. Every great scientific idea eventually reaches a boundary requiring something new. Newton's laws reached that boundary with light speed measurements and Mercury's orbit. Quantum mechanics and relativity reached it considering black holes and the Big Bang. Now we're at the boundary again, where Einstein's smooth space-time meets the quantum world of particles and uncertainty. Somewhere beyond that boundary lies the answer: quantum gravity theory. A description of Planck scale space-time, understanding of the universe's beginning, information paradox resolution, perhaps a unified theory describing all forces and particles, perhaps a multiverse, perhaps something we haven't imagined. Physicists working on these problems today stand at a cliff's edge, gazing into the unknown. They're using mathematics, creativity, and centuries of accumulated knowledge to build bridges across the gap. Some bridges will fail, some lead nowhere, but one might reach the other side. When someone finally figures out what space-time really is, it will change everything. So next time you use GPS, view a black hole photograph, or contemplate the Big Bang, remember, you're looking at one of science's deepest mysteries. You're seeing evidence of something we use but don't fully understand. An idea working perfectly in practice yet remaining mysterious in principle. Space-time is real. We can measure it, photograph it, detect waves moving through it, but we don't know what it is. And that's okay. That's where adventure begins. That's where science happens, not in answers already found, but in questions we're still trying to answer. Einstein gave us space-time over a century ago. It revolutionized physics, explained gravity, predicted black holes, gravitational waves, cosmic expansion. One of history's most successful theories. But Einstein himself would probably admit it's not the story's end, not the final answer. A step along the way, beautiful, elegant, powerful, but still just a step. The final answer is waiting. It's out there in the mathematics, experiments, observations yet to be made. Someone will find it, maybe in our lifetimes, maybe next generation, maybe centuries from now, but it's there. Thank you for joining this journey through space-time's mysteries. If this expanded your mind, smash that like button, subscribe for more cosmic deep dives, and share this video with someone who loves questioning reality. Comment below. What physics mystery should I tackle next? The universe is full of mysteries. Space-time might be the most important. Good night, and keep questioning everything.